Hello. I gave you this question at the end of the previous video, and let's calculate how to calculate. Let's see how to calculate this probability. So when I say when you consider the average of two dice equals 6, that means there is only one case in which both dice have 6, right? So the average, because 7 is not available, any number 7 or greater is not available. Uh, so to have an average of 6, it both have to be 6. And each of the dice has 1 over 6, 1/6 probability for this, and they are independent. Two dice are independent, so you can multiply those two probabilities, right? So remember, statistical independence imply, so we are considering probability that the first dice has 6 and the second dice has 6 at the same time. So then using the multiplication rule, which we studied in chapter 2, you can multiply the probability of each outcome, right? So here actually you can write it as intersection. And then the answer is 1 over 36. Alternatively, you can write down all 36 possible outcomes, right? There are 6 by 6 different pairs of outcomes, and if you calculate the average of each of them, then there is only one case which yields an average of 6. So 1 out of 36 cases satisfies the event. Therefore, probability is 1 over 36. So it's intuitive. And you may calculate, so this is just an example, and you may calculate any probability in a similar way. For example, probability that the average of two dice equals 5.5 can be calculated in a similar way, but now you have to consider two different pairs, 5,6 or 6,5. So out of 36 possible cases, two of them satisfy this event. Therefore, the probability is 2 over 36, right? So in this way, you can calculate the probability for any possible outcomes. And then I draw the histogram for the probability distribution. So let me start from the distribution for the experiment of throwing a single dice. If you throw one dice, it is just the usual experiment we considered in the earlier chapters, and then its histogram is pretty simple, uniform. Each outcome from 1 through 6 has the same equal probability of 1 over 6. So this is the probability. But if you throw two dice and calculate their average, then it becomes a sampling distribution. Previously, it is not a sampling distribution because there is only one observation from one experiment. But now you can call this a sampling distribution when you throw two dice. So throw two dice and calculate the average, then the distribution is a sampling distribution. And then I calculated the probability of 6 is 1 over 36, and 5.5 is 2 over 36. Like that, you can calculate probability at different points. Or you can just write down all 36 possible cases and classify them into different averages. Then you will get this form. And I can even increase the number of dice we consider. For example, I can do it on computer. It's not easy to do it by hand. So when you throw 5 dice at a time, so that one experiment has 5 observations now, then you can calculate the probability on computer like this. The shape is like familiar, looks pretty familiar, and if you increase the number of dice to 25, then it's even more smooth, like more smoother. So this is the sampling distribution, how the sampling distribution behaves and changes depending on the sample size, which is obvious. Depending on the sample size, the distribution will change, but there is a pattern. So 1, 2, 5, 25. So this is a simple computer simulation exercise, simulation experiment, and I did it on Excel. And I'm going to do a different experiments later. So what you can tell from those changes is that the sampling distribution is different from the distribution of a single outcome, right? So when you throw one dice, the distribution was flat, but when you throw 25 dice, it looks like this curve, right? And we are going to, and what we are going to do here is I'm going to generalize to see if this pattern is unique or like generic. So by considering unfair dice, I will simulate unfair dice for n equals 5 and 25. This is one hypothetical dice which has very large side for 1. So the outcome of 1 has twice more probability than the others. So it's like say, so the other outcomes have 1/7 probability each, but 1 has a probability of 2/7. So it's unfair. It does not exist in reality, but I can simulate that dice on computer. Think about this. Suppose that you have a strange dice like this, and throw that like there are 5 of them. 5 of them, and if you throw 5 of them and calculate their average, you will get this distribution, right? This is the sampling distribution if you throw 5 strange dice like this. And if you throw 25, it looks like this. Similar pattern. The pattern is pretty similar. Another strange dice. Now, I consider a different dice in which the lower outcomes like 1, 2, 3 are twice more likely to happen than larger numbers, 4, 5, 6, right? Probability doubled for 1 to 3 than 4, 5, 6. And then this is, of course, another strange, unfair dice. Hard to imagine how it looks like, but I can simulate that. And what's interesting here is when you throw 5 of them, you will get this distribution. You can think it as like I throw such dice on computer. Excel does the experiment for me, and when you throw 25 of them, when the sample size becomes 25, it looks like this, which also has a similar pattern, right? So what I want you to see here is the distribution for a single outcome does not matter. No matter what the distribution of a single outcome is, in the end it looks like this. Another experiment, another strange dice. Now I made up another unfair dice whose probability is proportional to the outcome. So 6 is 6 times more likely than 1. And 2 is twice more likely than 1. So probability increases as the outcome increases. Another imaginary dice. And what happens if you throw 5 of them? You get this distribution. What if you throw 25? This distribution. So it's amazing. So no matter where you start from, no matter how the dice looks like, in the end, the shape is the same. So we will extract common patterns from those experiments. So there is pattern 1. the expectation of x bar is the same as the expectation of a single observation. So let me go back what it means. So in this case, a single outcome has a mean at 3.5, right? It's obvious. So this is the center of this distribution, and this center does not change as the sample size changes. Center is always at 3.5. Same thing happens in these cases. Here in this example, green example, more probability is put on 1, so the mean is slightly smaller than 3.5. It must be like 3.2 or 1 or 2 maybe. So the center is here, and still the center does not change. Center is here, center is here. So the location of the center does not change, and location of the center does not change here either. And in this case, center is above 4, more probability is put on the larger outcome. So the mean is larger than 4, between 4 and 5. And then the sampling distribution has the same center. So the center is fixed from the single distribution. The single distribution, the mean of the single distribution is the mean of the sampling distribution. So the expectation of x bar is equals the expectation of a single observation. That is pattern 1. And pattern 2, the variability decreases. So the variability decreases and probability are more concentrated. Spread decreases. There are less spread. So it's clear. So in a single dice, you may get 1 or 6, but when you throw 5 dice, it is really difficult to have an average of 1. To have an average of 1, all 5 dice have to have 1, which is very unlikely. And it will be even more unlikely when you increase the number of dice. All the dice must be 1, which is very unlikely. So in the end, these extreme values become more and more unlikely, and in the end, all the probability will be concentrated near the center, which is common to any probability. Probability is becoming more and more concentrated. The range looks like shrinking. Actually, there is a very small probability here and there, but just there are too little probability there. So as a result, the variability is decreased. Same thing here. It will the shape is more decreasing, excuse me. The shape is becoming more and more concentrated around the center. So same thing here, same wide, but it becomes more steeper as the number of dice increases. That is pattern number 2. Pattern number 3, very clear. The shape of the distribution is approaching to the bell curve, and I told you in a spoiler, this is quite obvious. Bell curve, bell curve, bell curve, bell curve. It doesn't matter what is the first distribution. In the end, as the sample size increases, it will be bell curve. That is very interesting. These 3 are very interesting results, and each of these patterns becomes one theory, one theorem, and one law in statistics. Of course, very important law, because we can study so. As I said, the results are pretty simple. In the end, they are very useful because it means that the sampling distribution you don't need to worry too much about the mean, because it is the same as a single outcome. And we don't need to worry about the distribution because it is a normal distribution. And variability decreases as n increases, which will be also useful later. So I am going to make these three patterns into theorems in the next video. So see you in the next one.